Got it.
All right, welcome to the new forecast webinar forecast series. My name is David Margol, and I'm today's host. I'm very excited to introduce today's guest speaker and a good friend, Professor Paul Roundy. Dr. Roundy is an expert in tropical forcing. He studies waves of the tropical atmosphere and ocean and how these waves interact with one another and with atmospheric moist deep convection to modulate global weather and climate. In today's webinar, Dr. Roundy will talk about ENSO, and in particular, the application of ENSO for medium range and long range forecasting. The fact that we're moving into a third consecutive season here with La Nina makes this discussion all the more timely and interesting. In terms of the format, we'll ask that all of our audience members remain on mute, but we encourage you to submit questions via the Zoom chat, and we'll try to get to as many of those questions at the end of the webinar. Without further ado, I'm going to turn it over to Paul.
Thanks, Dave. So I was really interested in our first invitation to just present on tropical forcing overall, and I started to put together a presentation, and I just got overloaded. And it was really welcome, actually, when David sent me a request to change to focus mostly on ENSO this time and push some of the other content off to other times. So we're looking at El Nino Southern Oscillation. We're going to cover a basic background for the oscillation itself in order to understand its applications to prediction. And then we'll explain why it's more predictable at some times of year than others in the context of the things that drive ENSO to change. And I have to figure out how I'm going to move. There we go. I think I'm just going to use my my mouse and click to move forward. So let's say that we were on a ship over the North Pacific around 50 degrees north and 140 degrees west. And we had a thermometer attached to the hull of the ship and we were heading south. We would see the temperature rise from near 10 degrees C up to around 28 C at a maximum. This is where the intertropical convergence zone is located. And then in an average condition during most of the year, you would see the temperature drop as you go further south to the equator. So this is the equatorial cold tongue. And then there's a little broader warm region in the southern hemisphere, often especially during the southern summer. So this is November to December in this case, and then cool off again toward the pole. Now, this is the El Nino condition in its strongest, perhaps it's one of its strongest states ever. This is December 1997. We've had a few other events in the last century, including 1982, December, and 2015, wherein the cold tongue basically disappeared. And we're left with almost a temperature maximum on the equator, still kind of tabled level across the tropics. So the cold tongue is gone. And then you see the other extreme. This is from September 1998, developing La Nina condition, still warm from the previous El Nino event at the periphery, but cold anomaly has developed right on the equator. Now, of course, because of the economics impact of ENSO, we have installed these buoys across the tropical Pacific. Each one of them is moored to the ocean floor and has a set of instruments along its cable connecting it to the floor of the ocean. And then instruments on the buoy and up on a tower on top of the buoys as well. So we collect the data from these in order to track the progress of ENSO. And here's one particular temperature cross-section for average from those buoy data from 2 south to 2 north. This is August of the year 2000. It's kind of a neutral looking event. What you see is warm water floating on the top of the ocean, so the cold water down below. Longitude goes this way. It's across the whole Pacific Ocean, most of the Pacific Ocean. You see it's warmer in the west, cooler in the east. The trade winds blow this way in response to rainfall enhanced over the warm water. And the cold over here is a response to upwelling of cold water from below along the equator due to the rotation of the Earth. So westward force upwelling close to the coast in response to the land. This is a normal condition. An El Nino condition, a strong El Nino condition, might have the sea surface temperature reverse. And the warmest water in that case happened to be at the coast of South America, which is quite extraordinary. And here's a La Nina condition. In that case, the total amount of warm water volume in the basin is small, kind of isolated to the western basin. And this line right here of strong vertical temperature gradient called the thermocline has actually balanced and shoaled to the surface of the East Pacific. And this cold water upwelling comes to a balance in temperature in the East Pacific with downwelling radiation from the sun and exposure to warmer air in the region where the water is so cold. And of course, ENSO has a substantial effect on the winds in the tropics. And here is the situation where we have shaded is outgoing long wave radiation. I've subtracted the seasonal normals and we're left with active rainfall, more active than normal rainfall near and east of the dateline, a little bit going east to the coast of South America, and dry area in the warm colors here. And the vectors are the surface wind anomaly. You've got a ridge here and troughs poleward of the heavy rainfall and westerly anomalies. So this is denoting collapse of the trade winds. And here's a La Nina event. They're not quite symmetrical on average because the islands serve as a locus for convection here and make it more likely that La Nina is a more stable configuration because the islands favor convection. And this is where La Nina favors convection in that region. And so that's one reason why it's more likely to get multiple year-over-year La Nina events than El Nino events. If there had been an anchor of islands out here in the Central Pacific, then we would see something like that with El Nino as well. Now, it's not that it's impossible to have repeated year-over-year El Nino events. The early 90s had a series of events, but it's quite hard to get very strong events following each other.
That's great, Paul. I was just going to say, you already answered one of my questions. Thank you.
Yep. So here, this is from one of my papers in the Journal of Climate in 2015, showing the 1986 El Nino event development in longitude and time, shaded in sea surface temperature. The shading in each one of these panels is identical. It seems a little bit, maybe it wouldn't be so because of the contours on it, but the contours represent specific things. In the left panel, the contours represent the first empirical orthogonal function, the first EOF of sea surface temperature in the East Pacific. And what it says is this area is cold, this area is warm. This is the East Pacific eigenmode of sea surface temperature. It's basically, think of it like a seesaw. So either the East Pacific from the dateline east is warm or it's cold, and it goes all the way to the coast with a pretty substantial gradient just east of the dateline, and it's either cold or it's warm. That's what the pattern shows. In the middle panel, we have now contours of the second EOF of sea surface temperature. This is known as the Central Pacific eigenmode of El Nino. And in this case, you would see a warm Central Pacific and a cold Eastern Pacific. Now, the superposition between this one and this one can lead to signals favoring the Central Pacific or signals favoring the Eastern Pacific, and a whole spectrum of things in between. So we call the Central Pacific form of El Nino the Madoki, or El Nino of the other sort. It's a Japanese origin term for a different sort of El Nino. But people are all too, I think, excited about trying to categorize El Nino events as Central Pacific or East Pacific, when actually every event evolves across the course of its lifetime in stages that may be more Central Pacific or more East Pacific. While some events have more overall East Pacific and Central Pacific, it really isn't a good idea to try to label every event as if it was one or the other. Here's an example of an event. This is 2002, shown in the same eigenmodes. And you'll see the East Pacific mode strengthens in November and December. That's when it typically reaches its peak. But in contrast to 1986, this event kind of maintained the Central Pacific eigenmode going through the whole thing before and after the East Pacific mode maximized. And so now the superposition of these two says it's Central Pacific, expands to East Pacific, and then retreats back to Central Pacific across its lifetime. Now, here is a classic East Pacific event, December to February 1998. Here is a classic, the strongest ever Central Pacific event, December to February ending in 2010. This 2009-2010 was a classical Modoki Central Pacific El Nino event. The warm water is concentrated just east of the dateline. The warm anomalies go to the coast, but it's not stronger over here in an anomalous sense like this is. But now look at 2016, ending in February. What is this? The natural go-to was to call this an East Pacific El Nino event, but look what it is. It's bookended by the two extremes. Yeah. So it would be quite, I think, incorrect to try to say that every El Nino event can be sorted into this simple dichotomy. It can't. And if you actually compare, I don't have maps here, but if you compare the global atmospheric circulation signals associated with these different events, and you move between them, you'll find that the average placement of the jet off the west coast of North America, it was on the coast in 1997, just off the coast in 2015, and way off the coast in 2010. So where's my time at?
Oh, we still have a good 10 minutes.
All right. Okay, so it's obvious that ENSO impacts the weather around the world and the mean climate for months of a season that's dominated by one ENSO state. Predicting the signals associated with ENSO imply predicting ENSO itself, which is really easy at some times of the year and really difficult at other times of the year. And we can say that ENSO enhances subseasonal weather predictability during periods of time when it has a robust signal. What do we mean by a robust signal? Well, ENSO is easiest to predict when what we call the Bjerknes feedbacks dominate. The Bjerknes feedbacks occur when you have a climatological cold signal, in this case, that would have suppressed convection in the background, but then an El Nino signal superimposed on this that has now a substantially warmer than the climatology background rainfall signal here, that becomes associated with a wind pattern feeding into the anomalous rainfall, and it maintains the cold anomaly. So it maintains this cold signal here in the Eastern Pacific. So if you have El Nino in place, it's warm here and the winds are blowing in to feed it. And those winds are also pushing the thermocline down, maintaining the warmth in the area and therefore maintaining the rainfall. In the springtime though, the mean state looks like this. Toggle. So the difference between the warmest possible ENSO condition and the climatology is much, much smaller in April and May, than the rest of the year. And so there can be nowhere near as strong the Bjerknes feedback between the SST anomaly, the rainfall, and the winds that maintains a warm signal. So what it means is that this time of the year, nature goes toward wherever the subseasonal wind state directs it. So in fact, you'll see models waffling. Back in February, we were suggestive of patterns moving toward El Nino, and then there was a couple of months of strong trade winds. And this pushed the thermocline, but this brought the thermocline back up and resulted in reemergence of the cold anomalies. And kind of MJO westerly skipped a couple of months, and then they came back just a little while ago. And now the models have been edging a little warmer than they were before, as far as ENSO goes. The problem is that models can't predict subseasonal variability past a few weeks. So this makes predicting ENSO, which is going to follow the winds this time of the year, next to impossible at a long range. We may look at the models now and see that they're in common, that most of the models are going towards La Nina right now. And I think that that's probably true because we've missed the extra westerly forcing, but it's not necessarily so because the atmosphere could still produce westerly wind events in May and ultimately change the equation. So this time of year, the key interpretation is uncertainty. During the fall and winter, the key assumption is persistence. So if you can't predict those subseasonal signals very well, then ENSO can't be very predictable across the spring. I'm going to skip this for time. In order to understand how ENSO is evolving in response to wind stress, we need to think about the Kelvin wave, which is the way wind stress signals, wind stress responses in the ocean are translated across the basin. And we see on the equator here in the middle, and this is latitude and longitude. So we've got a ridge, eastward flow in the ridge, westward flow in the trough, divergence in between lowers the geopotential east of the trough, and the whole thing migrates toward the east. Now, this is a longitude time diagram of outgoing long-wave radiation data, 2004 into 2005. We have a classic kind of event of MJO coming in from the west and an equatorial Rossby wave coming in from the east. The two of them combine, and here you get enhanced convection and westerly wind. And then further east, later, you get this slow eastward moving rainfall region. And this region right here was actually associated with a downwelling Kelvin wave in the ocean. It's pushing the thermocline down, moving warm water from west to east. In order to understand these Kelvin waves, we need to look at how they cluster in real El Nino events. This is 2002 to 2003, and we're looking at a quantity called dynamic height anomaly. This is what buoys can give us that's the closest approximation of sea surface height. So a sea surface ridge, sea surface trough, time is going up. These disturbances are moving from west to east across the basin, and they have a phase speed associated with them. Each one of them is a little different. If I subtract the moving average and give the 2100-day Kelvin wave signal underneath, you'll notice that the earlier waves in a cluster tend to move faster. They slow down with time. They were forced in the west by MJO events. And so the time scale back here is 40 to 50 days or so, but it takes 70 days for a full cycle in the East Pacific because the events tend to slow down across a group. And here's just a time trace of 140 degrees west of sea level height in the blue, going up and down over time, and a cross section at the same time of zonal current measured from the tau array shows eastward flow in the ridge, westward flow in the trough. These are Kelvin waves because of that association between current and geopotential. Now here's the map I was showing you now with the Kelvin wave, downwelling Kelvin waves added. So you see MJO Kelvin wave coming out like that. So here is the 1997 El Nino event in outgoing long-wave radiation data. This is, you can see the longitude range here. Time is going up over the course of the event. Right here, it's not El Nino. Here, El Nino is developing, and here it's mature El Nino condition. And this is the winds over the Pacific. This is the dynamic height. Remember, proxy for sea level height. This is the 20-degree isotherm depth, which is how deep the thermocline is, roughly. And this is sea surface temperature. And we see MJO events go by. And they force Kelvin waves in the ocean, not very much change in sea surface temperature. Most MJO events don't make much difference in Pacific sea surface temperature. But as there's a little bit more warming going on here after this one, because it's warmer, the region can sustain more rainfall, which develops more westerlies. And then you end up with a stronger wave. And it's a positive feedback in the direction of growing toward the El Nino condition. When that Kelvin wave goes by, you get a warming of the East Pacific, but it's not really a strong El Nino event at that time. You wait till this event happens and you get one of the strongest westerly wind events in recorded history. Kelvin wave, and bang, we've gone to an El Nino condition within a couple of weeks. This is a OLR, active convection, atmospheric Kelvin wave during the El Nino coming across, and it forces a kind of MJO event and oceanic Kelvin wave in the red contours here again. This is how sea surface temperature evolves with the passing of those Kelvin waves. So the shading here is sea surface temperature, warm in the west, cold in the east. Kelvin wave goes by. Sea surface temperature jumps to a new mean state. Next Kelvin wave goes by. Sea surface temperature jumps again to the next mean state. So it's like stepwise, individual wave events are cooperating in producing a final evolution of the El Nino. But sometimes Kelvin waves don't behave that way. This background shading is winds, westerly wind anomalies, easterly wind anomalies. Here's a Kelvin wave in the ocean that was forced by westerlies, and it doesn't even make it across the basin because it intersects with easterlies. If you want to predict the evolution of El Nino in association with oceanic Kelvin waves, you need to predict the wind stress that the Kelvin waves will intersect with as they go. This is one of the complicating factors in understanding and making a solid prediction of what ENSO is going to do. Same pictures I showed before showing the development of the 1982 El Nino and OLR and the 1997 El Nino events. They're pretty similar in a lot of ways, right? What you see is the mean state convection is near the maritime continent, it's dry in the East Pacific, and then the El Nino develops, the East Pacific becomes moist, the maritime continent goes into a drought. Same thing in both. Couple of events. This really sets the cautious stage for making a prediction for how ENSO is going to evolve. Left side, shaded as OLR, you see MJO events, MJO event, MJO event, MJO event, MJO event. The red contours here represent westerly wind stress anomalies. These are westerly wind bursts. This MJO produced a westerly wind burst, produced a downwelling Kelvin wave in the ocean, and the right side shows sea surface temperature. In 1997, it shifts from cold to warm. Massive El Nino event forms. But look, westerly wind burst, westerly wind burst, westerly wind burst. Show you 2014. Now I don't have the Kelvin wave data for 2014 here. I haven't taken the time to download it. But series of westerly wind bursts. Ocean starts to change. Up to this point right here in April, they're basically identical. In fact, 1997 started from a colder initial condition. And it ended up going full El Nino, while 2014 just had a weak warm signal. Enough to influence the Atlantic tropical cyclone season, but look what happened. Westerly wind burst, 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 nada. So 2014 failed because the westerly wind burst activity ceased. Try to predict that. Now here's another extreme. I'm going back in time now to 1982. We don't have tau data that go back that far, but we have island sea level gauge data that also include the Kelvin wave data. And so I did a statistical reconstruction utilizing relationships between sea level gauge data and the tau buoy data. And oh, I went up instead of down. So here is, I created artificial missing data to attempt to show how my algorithm would recreate the wave state during this 2002 El Nino period. And this is the original data, and this is the reconstruction. A little weaker, I know the signal, right? Same phasing, it's virtually identical. So now I'm reconstructing the timing of the Kelvin waves back in 1982. 1982 was extraordinary because there weren't really major, this one right here isn't that big. This one is deceiving, it doesn't look big. These are Kelvin waves again. Shaded OLR, active convection, here's the MJO coming along. In early May 1982, there was a conference of oceanographers. One of them stands up and confidently says, this year, there will be no El Nino event because there isn't enough warm water volume accumulated. And so let's move on from assuming anything about this. Well, here it goes. MJO comes in just shortly after that. This Kelvin wave, and look at the active convection emerge right from there. And I go to the sea level height at Christmas Island. This is 1 north, 157 west, so right along the equatorial cold tongue. And going from the fall before into 1982 here, you see a few, minor Kelvin waves, they go by, bang, that event from this MJO is associated with a 20 centimeter shift in sea level height that then sticks around for months. In order to have predicted the 1982 El Nino event, you would have had to have predicted this upswing. Now, maybe if you had a good model that knew that this was a favorable time, maybe you could have predicted it starting a little earlier or a little later, but you have to be able to predict the mechanism by which it forms. We still do not do this very well this time of the year.
Hey, Paul.
So much.
Sorry to interrupt, but we're almost out of time.
Okay, so I've got just these slides left.
Sure.
And I wanted to show something associated with the models. This is called, it's a forecast drift, wherein if you're predicting 7 months out and it verified at 7 months out, you should get a maximum at lag 0. But instead you're getting a maximum at lag -2 or -3. You're getting verification of your 7-month forecast 2, 3, 4 months early. Sometimes it's so bad that the model doesn't know about the El Nino coming up until it's already forming because it didn't predict the westerly wind event that finally hit it and made it happen. This is why it's so hard to predict ENSO. These are correlation skill diagrams showing for forecasts initialized this time of year looking forward, the skill is negative. This is CFSV1, but I mean, all models are basically similar to this in terms of the basic structure. That you can predict ENSO really well when you're in the thick of a stable event, not when you're not. Same things. This is a statistical model, lead time going forward, showing forecast skill in terms of mean square error minimization. And this is January at 0, February, March, April. As you go forward, there's a hole in your ability to predict. But with this statistical model, you get almost as much skill predicting the next fall. This is a blind forecast set from a wholly independent data set. You're more able to predict what comes up in the following year than you are the following summer. The following cold season, I mean, you get more skill. the forecasts change. These are the recent CFS forecasts. Cold, but we've had westerly winds recently. The model starts to edge warm. And now they're going back because there's easterlies forming again, and the westerly winds will wag the dog. The models will go back and forth. And the reason why is background winds. They were models heading toward El Nino during the westerly wind events of January and up to February. And then we had trade winds enhanced. Then the models went toward La Nina. And now they started weakening the La Nina toward a warmer state, but not quite El Nino. But now the trade wind's coming back. So they're still trending more toward a cold signal. But there's no guarantee that we get a cold signal in August. It's actually possible that a westerly wind event emerges and couples with the sea surface, and we end up going toward El Nino. Persistence is the effective tool during northern fall through midwinter, with a few exceptions. Uncertainty is key in spring. There's altogether too much confidence. And maybe you'll find that you're right this time, but that doesn't mean skill. And this odd thing that the upcoming fall, using some statistical tools, might actually be more predictable than the upcoming summer. I need to put more study into how this could be. And that's all I have.
Well, that's great, Paul. Unfortunately, we don't have too much time. One question here, real quick. It's not really fair, but 20 years from now, how do you see things? Do you think we'll be able to get through some of these skill barriers that you've talked about, or do you think it's going to just be a very slow incremental climb here?
So I think what our models are likely going to do is over time, they'll improve in the way they simulate the kinds of events that yield change. So we won't be able to predict the specific forcing events and so exactly where it's going to go, but we'll be able to better represent the range of risk. And we can see this now in how models have evolved since the 1990s. Climate models in the 1990s that had ENSO were almost perfectly cyclic. See, ENSO has internal, this reflection and the wind forcing, it all wants to go back and forth and be rather predictable. The reason it's not is the weather. The weather changes the forcing that can change the direction of ENSO. And ENSO influences the weather, but doesn't control it. So back then, they had no capacity to simulate the MJO, tropical cyclones, anything else. And so I think that in the future, although we can't predict the MJO 2 months out, we will be able to predict the range of possible MJO outcomes, and then so better represent risk. And so maybe our models won't wag around so much as they do now in terms of the ensemble means.
Okay. All right. Well, yeah, so many questions, so little time, unfortunately. But, Dr. Roundy, thank you for spending time with us. I really hope our viewers found this as interesting and informative as I did. And I really hope we can have you back soon, not only to talk more about ENSO, but to talk more about some of those other tropical forcing signals you mentioned, like MJO, Kelvin waves, Rossby waves. There's so much more there. Finally, for those who couldn't make our video today, we will be posting all of our videos on the YouTube channel. The link is in our MailChimp. So once again, Paul, thank you so much. And thank you for being here.
You're welcome. Thank you.